Hello everyone. In this lesson, we're going to discuss preparing numeric data for analysis. Now, numeric data tends to be better behaved than text data. There's only so much that can go wrong with numbers, whereas text can have all sorts of different symbols and Unicode characters, emojis, so it tends to be messier to work with. But despite its relative cleanliness, there are still a variety of pre-processing tasks you may wish to consider before using numeric data to prepare it for analysis and use in predictive models. The first operation we'll learn about is centering and scaling. Numeric variables are often on different scales and cover different ranges, so they can't be easily compared and used in predictive models that give more weight to one variable than another due to the scaling differences. Centering describes setting the central or mean value of the variables to the same thing. Typically, you would set it to 0. And scaling describes setting the variance or standard deviation of numeric variables to be the same. By centering variables and putting them on the same scale, you're not going to have certain variables that happen to be on larger scales dominating your analysis or predictive modeling. So a common way of centering variables is to set the mean for the numeric variable to 0. And to do that, you just subtract the actual current mean from all of the values. So we'll show how we could do that below. We just need to import some packages here. And for this lesson, we're going to be using the mtcars dataset. I have uploaded this to Kaggle so that we can work with it. It's just a data set with some numeric variables on some different vehicles. So when we run this, we can see that we have some different cars loaded in, and we also stored the means for the columns in this variable colMeans. We did that by getting the sums and then dividing by how many cars there are. So we'll look at those values below, and we can see here we have a bunch of different numeric columns, but the average value for each of these columns is quite a bit different. And since we have the column means in hand now stored in that variable, all we need to do to center the data is just subtract those means from each row in an element-wise fashion to center the data at 0. Since Pandas performs math in element-wise fashion and on a row-by-row basis by default, all we actually have to do is just subtract those column means that we calculated from the data frame. So to do that here, we can say mtcars minus the colMeans that we calculated. We'll resave that as centered, and when we run describe on it to get summaries, we can see here that in the summary, the means of all the columns now are very close to 0. Some of them aren't exactly 0, but they're essentially 0 for all of them. Now that the data is centered, we'd also like to put it on a common scale. One common way to put data on a common scale is to divide it by the standard deviation of the data. Now, standard deviation is a statistic that describes the spread of numeric data. It is equal to the square root of the variance. So you can kind of think of variance and standard deviation as being two sides of the same coin, but with either of them, essentially you're talking about how spread out is your data, meaning how often do you see data values that are, say, significantly higher or lower than the mean. In some data sets, you have your data very closely or tightly clustered around a typical mean value, whereas in other data sets, your distribution might be very spread out, which means it would have a higher variance and therefore a higher standard deviation as well. So to scale our data using the standard deviation, we need to get the standard deviations for each of the columns, and then we can simply divide our existing data frame by those standard deviations, and we will get the scaled version of the data frame. So we'll show how to do that here. We'll do mtcars.std axis 0. That will get us the standard deviations of the columns. Then we will take our centered data and divide it by those standard deviations. So let's run this and hit .describe. And now we can see that in addition to the mean essentially being 0 for all of these values, the STD, standard deviation, for all the numeric variables is now set to 1 for each of them. So manually centering and scaling the data like we just did here is not particularly difficult, and it's a good exercise just to think about what centering and scaling the data even mean. But you can do this without having to manually write out these calculations using functions built into a popular Python machine learning package called Sklearn. So we'll show how to do the exact same centering and scaling we did above just by loading in Sklearn and using its preprocessing module to do it instead. So below, we're going to, from Sklearn, import the preprocessing module. So we'll run that. And then to center and scale, we simply want to run preprocessing.scale on our data set. That will run essentially the same preprocessing steps we just did on our data and then save it as a NumPy ND array. Since we want a data frame, we'll then take the resulting ND array and just cast it as a data frame here by running pd.dataframe and passing in that scaled data. And when we do that and run.describe again, we'll scroll down here and see that just like before, our means here are essentially 0. So close to 0, they might as well be 0. And the standard deviations are all essentially set to 1. After centering and scaling your data, another thing to ask when you're working with numeric data is whether you have variables that are heavily skewed. So the distribution of a numeric variable, which is its overall shape and how the data is spread out, can have a significant impact on your analysis and modeling. In fact, kind of the whole purpose of data analysis is to investigate why the data varies the way that it does, and then exploit that observed variation in order to draw interesting conclusions or perhaps make models that are able to project that variation to make better decisions in the future. Data that is roughly evenly spread around the average or mean value, with most of the values being clustered around the mean, is known as normally distributed data. And data that exhibits a normal distribution tends to be well behaved. On the other hand, some data exhibit significant skewness or asymmetry, where perhaps there's a number of data points that lie significantly above or below the average value. To illustrate this, we're going to generate a couple plots of data with different distributions. So we're going to start by generating some normally distributed data. What we're doing here is generating 10,000 values from a normal distribution. That's what random.normal is doing. And then we're just going to make a histogram of it to look at what the distribution looks like. So normally distributed data looks something like this. You have the average value in the center, and the average is very close or essentially the same as the median because you have an even number of values on either side of where both the median and average are. Another characteristic of normally distributed data is this kind of bell-shaped curve that goes up and down with many values centered near the average, and then these tails where being further and further away from the average becomes increasingly rare. So you can see that most of the data is actually within one standard deviation of the mean. The mean here is 0, and between -1 and 1, these two bars here contain the majority of the data, and being further than one standard deviation from the mean is actually somewhat uncommon. And once you get past, say, 2 or even 3 standard deviations from the mean, now those are getting to be quite rare values. So numeric variables with this sort of general shape are nice to work with because they conform to various assumptions that you might be making in your analyses and predictive modeling. For instance, if you're using a modeling technique like linear regression, which is a very common way of making predictions on a numeric target, there's an assumption that your target variable is normally distributed. So if it isn't, your model is more likely to produce bad results. So next we'll look at an example of data that isn't normally distributed. We're going to sample some data here from the exponential distribution. You don't have to worry about what that is yet, but essentially it's going to make data that is skewed. So let's run this and just look at the skewed data. you can see in this case, the more common values are clustered near 0, but there's this long tail of more rare values that go way off to the right. In this case, the data then would be called right skewed or positive skewed because the values are trailing off to the right. If it was the other way around and going off to the left, it would be called left skewed. So if this was a variable we were interested in making predictions on using a numeric technique like linear regression or perhaps neural networks or something like that, we would probably be interested in reducing this skewness so that our model might produce better results. One transformation we could apply is the square root. That will tend to squash the data a bit and make it look a bit more normal. So we'll show how we could do that. All we need to do is apply the square root function to each of the values. To do that, we can take the data, skewed, and then say dot apply. That is a pandas method that will apply a given function to the data frame that you're passing in. So here we're passing in the skewed data we made. We're going to dot apply this function to it, np.square root. So we're applying the square root function that's in the NumPy package to our data. That will get our square root transform data. So then we're just going to take this transform data and plot it again so that we can see the difference that applying this transformation made. And you can see that after doing the square root on all the values, the distribution looks a lot more like the normal distribution now. We have a bit of a bell-shaped curve now, and most of the data appears clustered around a central value. Another transformation you can use to reduce skewness of data is a log transformation. So I'll show an example of doing that below. So to do that, we're going to take the data, add 1 to all the values, and then to that we're going to dot apply, this time the np.log function. Now the reason we added 1 to the data is that if you run log on a value that's less than 1, you're going to get something negative, and if you run it on something that's 0 or less, you're actually not going to get a real value. So you want to generally make sure that the numeric values you're trying to apply log to are 1 or greater, so that's why we're doing this. And after we save that as log transformed, we will make another plot. So again, we have created a distribution that looks a bit more normal than what we had before. It does cut off pretty strongly at 0 here, whereas the square root transformation actually didn't have that drastic cutoff. So in this case, the square root transform might actually be better, but in either case, we've managed to reduce some of that obvious skewness that we saw before. And note that if you're doing a transformation like this to transform a target you're doing some kind of modeling and prediction on, after you have run your prediction, you would probably want to convert that value back to its original scale. So in the case of the square root transform, after making your predictions, you would square them all to get the actual values on the scale of the original data. And for this log transform, you would then want to apply the exponential function to it to undo the log function, and then subtract 1 to undo the +1 that we did before. Now, another thing to look out for when you're working with numeric variables are highly correlated variables. In predictive modeling, each variable you use to construct the model would ideally represent some unique feature of the data that doesn't have much connection to the other features. In other words, you want each variable to tell you something different. In reality, a lot of variables often exhibit collinearity, which means they have a strong correlation or tendency to move together, typically due to some underlying similarity or common influencing factor. And when you have these sorts of strong correlations between your variables, they can interfere with one another when performing analysis and predictive modeling and can screw up your results. To check the correlations between our different variables, we can use the .core method here. So we're just going to take a slice of our first 6 variables and then check their pairwise correlations with .core. So we can see from this resulting matrix here, we have some pretty significant correlations between the variables. Now, correlations run on a scale from -1 to 1. A correlation of 0 means the variables are not related at all. A correlation of 1 means two variables are perfectly positively correlated. A positive correlation means when one variable goes up, the other variable tends to go up as well. A correlation of -1 would be a perfect negative correlation. A negative correlation means when one variable goes up, the other tends to go down. In this case, we see some fairly large correlations, either positive or negative. For instance, the MPG variable, which is the miles per gallon a car gets, looks like it has a negative 0.85 correlation with the number of cylinders. That means there's a fairly strong correlation between cars that have more cylinders having lower MPG. Similarly, horsepower has a negative 0.77 correlation with MPG. That means cars that have better horsepower tend to have worse miles per gallon. And there's even a correlation of 0.9 between cylinder and disp or displacement. Well, that makes sense because engine displacement is the volume swept out by the pistons in the cylinders of a car's engine. So since displacement is directly related to the car's cylinders, it would make sense that cars with more cylinders also have more displacement. Another tool for inspecting this sort of correlation and collinearity between variables is a scatter plot matrix. So we'll show how to do that below. Essentially what it's going to do is for every combination of values, it's going to generate a scatter plot, which might be easier for us to look at and quickly find these sorts of correlations without having to read a numerical table. So we'll show how to do that here. We're going to say from pandas.tools.plotting, import scatter matrix. And then we're just going to run this scatter matrix function on those same first 6 columns. We're going to set the figure size to 10 by 10. And this argument, diagonal equals KDE, will show estimates of the distributions across the diagonal of the resulting scatterplot matrix. So we'll just run this and show you what it looks like. So in the resulting scatterplot matrix here, each of these cells shows a scatter plot between two different variables. For instance, this one right here shows disp or engine displacement plotted against MPG or miles per gallon, where higher engine displacement values up here tend to be associated with lower miles per gallon in your car. And along the diagonal here, we just have distribution estimates for each of the individual variables. So looking at something like this can perhaps allow you to spot interesting relationships between the data easier than you could just by looking at raw values in a table. For instance, here we can see that the cylinder variable actually only takes on 3 distinct values. There's values at 4, 6, and 8, but this isn't a continuous variable where we have points all over the place. So although in this case cylinder is encoded as a numeric variable, you could perhaps also consider cylinder to be a category because there are only 3 different values for it, either 4, 6, or 8 cylinder cars. So if we are doing data analysis or modeling on this data set, it could be a reasonable thing to do to convert this cylinder variable into a categorical variable instead of having it be a numeric one. Now, if you do find highly correlated variables in your data set, there are a few different things you could consider doing to them. You could just leave them be and accept that you're going to have some in your data set. You could perhaps remove some of the highly correlated variables, or you could try to combine them in some way so that you have a smaller resulting data set that doesn't have so many highly correlated features. Reducing the size of the data set, either by throwing out variables or using some other technique to combine them in some way, is known as dimensionality reduction. Now, in our previous lesson on data exploration, we looked at the Titanic disaster training data set and found that some of the passengers were missing values for age. Missing values in a numeric variable can be troublesome because you can't simply treat them as another category. You either have to remove them or fill them in with some other value. Filling in missing numeric values is known as imputation, And the sklearn package that we used earlier has an imputer function that allows you to impute or fill in missing values with different functions. So below we'll give an example of using this imputer functionality to fill some missing values with the mean value. So below we are going to say from sklearn.preprocessing import the imputer. These lines aren't too important. They're just putting some missing values into this empty cars dataset because it doesn't have any missing values yet. So we're going to say where the MPG values are greater than 22, we're going to set those ones to none, so they'll be missing. So that will introduce some missing values into our data. We'll run it here and note that we do have some none missing values. So now we can use our imputer to fill those back in. So to fill the missing values we introduced with this imputer function, we want to call the imputer. We want to direct it to what our missing values are. They are not a number of values. We want to say how we want to fill them. In this case, we're going to fill them by the mean value. So we're going to set strategy equal to mean for the mean value. And then we want to fill them by column. So we'll say axis equals 0. After we run this and save it, we can use this saved imputer to fit and transform our data. So to do that, we take the imputer that we saved, say imp.fitTransform. We will run it on our empty cars dataset, and that will recreate the dataset with those missing values filled by the mean. Now again, this is stored as an ND array, so we're just going to run some extra code here to convert it back to a data frame. And when we run this and look at the first 10 entries, missing values have now been filled in with the mean, which appears to be about 17 miles per gallon. So this imputer function that we use supports imputing with the mean value, the median value, and the most frequent value, which is known as the mode. There are other methods for imputing values based on similar or neighboring records. That uses other columns in your data to try to impute values in the column that has missing data. This is something that you can do, but essentially when you're using something like a k-nearest neighbors model to impute data using information from other columns, you're essentially using a predictive model to fill in your values. And then if you're going to use those imputed values to make another predicted model to perhaps try to project some target variable of interest, well, you're essentially then making a predictive model out of values that themselves were generated from what amounts to a predictive model. This sort of layering of different modeling techniques on top of one another can significantly increase the complexity and processing time of your model and may not necessarily yield any better results than filling with some common value like the mean. So I would generally avoid using some sort of complicated imputation method unless you have good reason to think that something like a k-nearest neighbors imputation would do a better job than something much simpler like filling with the mean or median. So in the past 2 lessons, we've covered a variety of methods for preparing both text and numeric data. Now, the majority of the data you're likely to encounter will fall into one of these 2 categories, but there are other data types out there that occur with enough frequency you're going to have to deal with them sooner or later. One of those data types are dates. So in the next lesson, we're going to learn the basics of dealing with dates in Python. If you found this video useful, drop a like, hit subscribe, and I will see you again next time.